plan, I'm going to walk you through the notion of constraint programming, just with a short introduction. And then we will solve some combinatorial problem using constraint programming method. And after that, I will explain on a very high level the implementation details of the constraint programming solver, and that will help us to justify why Beam platform is a very good fit for constraint programming. And in conclusion, I will talk about where we are at right now, and what are the challenges, what is the future work, and what if you want to use constraint programming right now on Beam platform. Okay, so the constraint programming is focused on solving combinatorial problems, and the method is to formulate the problem as a set of constraints. The origins of constraint programming are in Prolog. First constraint programming solvers were written in Prolog 2, and there was a big influence from AI research on image processing and computer vision. A lot of successful applications in industry, business, manufacturing, and science. Things like planning, resource allocation, logistics, very popular in supply chain, all kinds of scheduling, network optimization, analysis of computer programs as well, and many more applications. So we have two classes of problems in constraint programming. First class is constraint satisfaction problems. What it is, we are given a set of decision variables along with their domains and a set of constraints over decision variables. And we want to find solutions, and solution in constraint programming is represented by an assignment of the values to decision variables such that all constraints are satisfied. Second class of problems is an extension of constraint satisfaction problems. Same thing, but we also are given an objective. The meaning of it is that not only we want to find solutions, but we want to find the best solutions in the sense of an objective function. Usually we want to minimize or maximize some objective function. I think that it may sound a little dry, so we'll go to our first motivating example. Here's XKCD comic. Here's on the bottom, there is a thorough explanation of what is going on here, but what is the story? We are at restaurant, the customer looks at appetizers menu and makes some exotic order. Rather than ordering by appetizer names, the order goes by the total price of the appetizers. And of course, it's a combinatorial problem, and the waiter, and it's time consuming. So obviously the waiter is not happy about this because there are 6 more tables to serve. And customer is trying to be helpful, but unfortunately, his suggestion requires to solve another combinatorial problem. So we have 2 combinatorial problems in this story, and we want to help waiter. And we will help waiter using constraint programming. So what do we need? We need to put together some models. Model in constraint programming is combination of constraints, decision variables, and additionally, if the problem is an optimization one, we will have an objective. And of course, we need some piece of software, a capable constraint programming solver, and we will use Fixpoint. It's an experimental solver written in Elixir. I am a maintainer, and it's pretty immature project, but it already has some capabilities. Here's the link to XKCD LiveBook. You can run these examples if at home if you want. It's runnable LiveBook. Okay, but in general, before we start looking at the model, how do we solve problems with constraint programming? So the very nice feature of constraint programming that we are not actually we do not have to program. It's not a programming in the sense of conventional programming. We do not put any we do not put together any algorithms or any kind of heavy computation by ourselves. Everything is done by the solver once we are able to model the problem in terms of constraints and decision variables. So I have to quote a prominent computer scientist, Eugene Freider, and I'll read it as this: constraint programming represents one of the closest approaches computer science has yet to make to the holy grail of programming. The user states the problem, the computer solves it. So that's as simple as this. We create a description of problem and our job is almost done. Okay, let's go back to first problem on the XKCD, choosing appetizers. So just to remind you, customer wants exactly 1505 of appetizers, and this is a constraint satisfaction problem. In combinatorics, it's known as subset sum problem, which is a special case of knapsack problem, and it is NP hard, meaning that it has exponential computational complexity. Let's just skip over to the model. So how does it look? We have data, obviously, which is a list of appetizers along with the prices. We have a total that the customer required us in the order. We declare the quantities. The quantities will be our decision variables. And what we have to do, we will, for every variable, we need to define a domain. And this 0 to this expression means that we can decide not to choose appetizer at all, or we can fill the order, fill the total with the appetizers, so to decide to use maximum possible amount for the appetizer quantity. So we'll work out price quantities. We'll need them for the constraint. And finally, model here will have our variables, decision variables, and a single constraint sum, which enforces that the sum of priced quantities will have to be exactly a total price. That's it. That's all the programming that it's not even a programming, it's just a description of the model. And we are almost done. All we have to do is to feed our model to the solver, and the solver just produces solutions. We have exactly two solutions. Solver thinks that it's done, so we don't have any more. And this is some kind of logical inference that the solver does behind the scene. Second part, serving tables as fast as possible. And just to remind you that we have seven tables in total, and we want to find a route for the waiter to serve this table as fast as possible. This is a constraint optimization problem because we also have, on top of the constraints, we have an objective, and this is a traveling salesman problem in disguise. It's also NP hard. And let's skip over to the model. Okay, here I had to, okay, there's 7 tables, and I had to just make up table coordinates just to make it more interesting. It's not those coordinates is not in XKCD, but yeah, I just did it. So TSP model needs distances as an input, and yeah, it's a packaged model. You can look up the details in that LiveBook how it's done. I just put this packaged model for brevity. We feed it to the solver. Solver finds us solutions. We pick the best solution, and we visualize the route. And here's our instructions for the waiter. This represents the shortest optimal route. And we are done with XKCD. We were able to help waiter to solve the problems. And let's go to a few more examples. These examples, as advertised in the title of the talk, there is a LiveBook for these examples as well, so you can run them if you want to try. So first example, reindeer ordering. This problem was posted on decision management community website a few years ago around the Christmas time, and it asks us to order reindeers according to some rules. We have 15 rules, and this is not a hard problem to solve by hand, but personally, I do not solve puzzles by hand anymore. I would prefer to put together the model. Personally, for me, it's actually more fun rather than solving manually to just use Elixir for solving. So what are our decision variables? Our decision variables are positions for each reindeer. And the constraints is a bunch of x less than y expressions for each reindeer. Reindeer x follows reindeer y rule. The model is pretty simple. We have positions as decision variables. We define domain for each of them. The domain here, this definition means that any reindeer can be placed on any position before we start logical inference with rules. The rules here are almost, the very straightforward translation from the problem description. As you see, we just use behind and in front of functions just for convenience. Each one produces a list of less constraints. And in the model, we have positions as variables, and we have rules, of course, and we also have all different constraints just to make sure that no two reindeers end up in the same positions, and no reindeer will appear in two different places. So that's what all different constraint is for. And again, we will feed this model to the solver, and the solver produces the result. Okay, two more examples. N queens. It's a very well-known problem to put n queens on n by n chessboard such that they do not attack each other. Decision variables are for each column we want to decide on the row to position the queen. For example, for column 1, we decided to put queen on a row 2, and yeah, so far so forth. And the constraints are just chess rules. So it's also pretty straightforward to translate the problem statement in the constraints. I'm not going to show the code, but yeah, you can check it out again here on a Fixpoint GitHub. Sudoku. We all know what it is. Just in case, I will reiterate the rules. Fill up the empty cells in 9 by 9 grid with numbers from 1 to 9, such that every row, column, and 3 by 3 block have different numbers. So again, it's pretty straightforward to see what decision variables are. So for each empty cell, we want to decide on the number from 1 to 9. And constraints are, again, just Sudoku rules. Again, the source code is available on Fixpoint, and this picture was actually produced by LiveBook. Okay, so now that we have an idea of what kind of problems we can solve with constraint programming, the question is, how does all of it works? How constraint programming solver does its magic? And I have to mention here that brute force is usually not an option for any for solution of any combinatorial tasks, and definitely the solver does not do brute force. It does much better than that. So yeah, in principle, we can enumerate all solution candidates and check them against the constraints, but it's like it could be a disaster for even the small-sized combinatorial problems. So the solver is smarter, and there are two things that the solver employs. First thing that solver will do is the filtering. Trying to remove nonsensical values from the domains, the values that couldn't be part of any solution given the constraints. And once the solver is done with this, it goes on to branch on the variables, meaning that it splits the problem into sub-problems, and then goes on filtering on the branches, on the sub problems. So it's you can visualize it as walking down the search tree, but with the filtering. So on every single step, the branch loses the domain, some part of domains, and the problem becomes easy when we go closer to the bottom of the search tree. Just to illustrate it, a tiny example. We want to solve x less than y, given two variables, x and y. Each variable has 3 values in its domain, and we want to find all possible solutions. So filtering, the first step the solver does. Looking at the domain, the solver realized that x equals 2 and y equals 0 cannot be part of the solution, so we can knock them down. And we will end up with reduced domains like so, two domain values for each variable, but that's as far as the filtering can go at this point. And so the next step is to make decision and branch. So usually the solver chooses a variable and then picks up the main value from this variable, and then it branches on it. So for example, here we can decide to branch on x equals 1. So that will result in 2 branches. Again, you see how x, the domain of x is split now. And then we go on with the filtering for each branch. For filtering for branch 1, we can notice that we can get rid of y equals 1, and that will produce a first solution for us. Then filtering for branch 2, nothing to filter here, unfortunately, so the solver will do branching again on y equals 1, split domains again, and this produces 2 more solutions. And yeah, you will see just what have we done here. Blue circles are nodes we did the branching on, and diamonds are solutions. But yeah, that was a simplified example, just one constraint. What happens if there are many constraints? Then the solver will start a propagation process. So meaning it will pick up a single constraint, thus filtering on it, and then all the changes that result in this filtering will be pushed to related constraints. Those constraints in turn will do more filtering and push the changes back. So you can visualize it as some kind of collaborative network of constraints. And this goes on until there's no more changes to be done. And at this point, we are saying that it's a fixed point or stable state. And then the solver goes on with branching. And then, yeah, as we already said, it will be repeated recursively. So now that we know on high level how it all works, how do we justify BEAM for constraint programming? And here we have solid support from computer science. Here's a textbook that probably some people are familiar with, written by Peter Van Rooij and Seif Haridi. Chapter 12, Constraint Programming, describes the constraint-based computational model, and this is, in a nutshell, a very detailed description of the flow that we've seen on previous slides. So it's a filtering starting from the top. It's a filtering propagation after reaching fixed point, and then branching into subspaces, and the process goes on recursively. So the upshot from the book is that execution in the computational space could be implemented with the maximally concurrent model, meaning that each propagation can run in its own thread, and each subspace can be executed concurrently and independently of other subspaces. So that statement will probably make you think about BEAM, concurrency. But the concern is that such models usually are difficult to implement, right? We can have problems with maintaining data consistency. We can have problems with the order operations if they matter. But fortunately, those concerns are not applicable for this particular model. Why is that? First thing, with the filtering, first part of it, filtering only removes domain values and nothing else. We do not modify data. We don't add anything to domains. So the domains always go down in a monotonical manner, and that gives us a chance to have concurrent conflict-free filtering. So meaning that the concurrent filtering on the domains will not result in data inconsistency, and the result of filtering will not depend on the order of operations. Those are very beautiful consequences for us. And the second part of it has to do with the implementation. Usually, when we do branching, we create each branch will have its own reduced copy of the parent branch state, and when branches go apart, they do not share anything between each other. So that gives us opportunity to do subspace search concurrently, and concurrently it will be conflict-free. So these two things give us massive opportunities for scaling. So we can scale at will. We can do parallel filtering, we can do parallel search, we can do both of them, and we can do all of the above on multiple nodes distributed solving. And another concern is how about number crunching, because we know that the combinatorial problems are computational heavy. Yes, that's true, but we don't do arithmetics there, almost never. So this is not a concern. In linear programming, machine learning, approximation methods, this is a big concern, because we have usually a lot of fixed point operations, arithmetic operations, but not in this particular model of constraint programming. So what are challenges, and where we are at now? So the challenges are related to functional programming approach, right? For example, for domain operations, the systems with mutable domains, mutable domain operations perform better in general. We do not. So this is a problem that we have to work on. Another big problem is the filtering algorithms, and this is filtering algorithms are often non-trivial, so there is a lot of work to be done here. And So what about Fixpoint library? It's an active development. It's a proof of concept. Please do not use it in production. And lots of work to be done. Please join me if you want, if you're interested. I will appreciate it. There is another library called Solver. If you need to use constraint programming right now, it's pretty safe to use. It's been used in production by some companies. So you can contact me, and I'll tell you more about it. So yeah, it's a safe option which uses mini-zinc system. It's an integration platform for constraint programming solvers. Okay, so that concludes my talk. Thank you very much for attention.